So here is another question on displacement current in parallel plate capacitor. So it is given that a parallel plate capacitor of plate area A and plate separation D is charged by a constant current I. Consider a plane surface area A by 2, that is half of the capacitor plates, area of the capacitor plates. It is placed parallel to the capacitor plates and situated symmetrically in between. Determine the displacement current through that area, that surface area A by 2. So here first let us understand. So here basically it is saying that we have a parallel plate capacitor arrangement, okay, this, and in between we have another plate, okay. Here the area is A by 2, okay, and here the plate area is A. Now we have to find the displacement current through this area. So the basic definition of displacement current, so first one is ID is equal to epsilon 0 d phi E by dt, that is epsilon 0 absolute permittivity multiplied with the rate of change of electric flux with respect to time. Then another one is ID is equal to epsilon 0 A dE by dt, and then we have ID is equal to C dV by dt, capacitance and rate of change of electric potential. Here epsilon 0 A, rate of change of electric field with respect to time. Okay, so here the gap is D, plate separation. So here I think we can use the first one, okay, this first equation can be used. So let us see how we can do it. So first remember, here this is charged by a charging current of I, okay, a charging current of I. Okay, now if you see, we have Q charge in a parallel plate capacitor, that is equal to CV. Okay, basic definition. We can write this as C as epsilon 0 A by D into V, this, okay. Then we can write V by D is equal to Q by how much? Epsilon 0 A. Now if you know, if you remember, voltage per unit length or separation distance in parallel plate capacitor, that is equal to the electric field, okay, the electric field intensity. So the electric field intensity here is equal to Q by epsilon 0 A. Then flux is equal to how much? Electric field intensity into area, okay. So through this small area A by 2, flux will be equal to electric field intensity into A by 2, okay, A by 2. So that will be equal to Q by epsilon 0 A into A by 2. So A will get cancelled, so we'll have only Q by 2 epsilon 0, okay. Electric flux through the small area, electric flux through the small area A by 2 is equal to Q by 2 epsilon 0. Now displacement current is how much? Epsilon 0 d phi E by dt, rate of change of electric flux with respect to time. So here it will be d phi A by 2 by dt for the small area. So that is equal to d by dt of q by 2 epsilon 0, which is equal to 1 by 2 epsilon 0 dq by dt. Now dq by dt is nothing but what? Current. Okay, so here it is equal to how much? d phi by dt, epsilon 0 d phi by dt. So another thing I missed here is epsilon 0, okay, d by dt of this much. So here it is epsilon 0, here it is epsilon 0, so epsilon 0 gets cancelled, so there will be no epsilon 0 here, okay, there will be no epsilon 0 here, only 2, 1 by 2 into I, okay, so it is I by 2. So the displacement current through the small area, okay, through the small area A by 2, which is placed in between the two capacitor plates, that is equal to half of the charging current or conduction current. So here I missed this, okay, by mistake I forgot to write this epsilon 0 absolute permittivity before, that's why. So here epsilon 0 gets cancelled in both the numerator and denominator, and we have only I by 2, that is the conduction current or charging current divided by 2, that is the displacement current.